Did you know that each year the world harvests over 60 million tons of mangoes? That's an absolutely staggering figure, enough to cover an area the size of Miami, Florida, or fill over 2 million semi-trucks bumper to bumper. But those aren't just numbers. They represent billions of sweet, tropical fruits that embark on a massive, hidden industrial journey to reach kitchens and tables worldwide. Forget the simple fruit stand. Get ready to dive deep into the colossal scale and amazing technology behind how millions of tons of mangoes are processed every year. This incredible journey begins in the vast, sun-drenched orchards of the global tropics, places like India, Mexico, Peru, Thailand, and many others. These aren't small family plots anymore. They're meticulously managed industrial farms covering thousands of acres, cultivating specific mango varieties optimized for flavor, texture, and yield on a massive scale. Growing mangoes here is a long-term commitment. It takes anywhere from 18 to 24 months for a single mango fruit to develop from a delicate flower into a mature, ready-to-pick fruit. As those heavy, golden or blush-colored fruits ripen on the branches, often protected by paper bags right on the tree to shield them from pests and harsh sun, the harvest season explodes into action. Harvesting millions of tons of delicate mangoes from trees that can reach 30 to 60 feet tall is a huge logistical and physical challenge. Mangoes bruise incredibly easily, and their sap is highly acidic and irritating. Because of this fragility, much of the harvesting is still done by hand by skilled workers. They climb ladders or use long poles equipped with special cutters and collection bags, carefully detaching each fruit to prevent drops and bruising. Even with modern mechanical lifts raising workers into the canopies, the final crucial touch is human. A blend of traditional skill and new technology to handle this precious, delicate cargo. Right after picking, there's a critical step that's often overlooked. The spot where the mango was attached to the tree, the stem end, can ooze sap. This sap isn't just sticky, it's highly acidic and can burn the fruit's skin, causing black marks and ruining its marketability. So, immediately after harvest, the stem end of each mango is quickly treated, sometimes dipped in water or rinsed to neutralize and wash away that corrosive sap. Then, the mangoes are carefully packed into sturdy, ventilated plastic crates designed to protect the fruit and allow essential air circulation. Speed is paramount to preserve freshness, as these tons of valuable, delicate fruit are quickly loaded onto trucks, beginning their journey from the farm towards sprawling high-speed processing facilities. When those trucks arrive at the factory gates, often lined up for unloading, the sheer scale of the operation hits you. This isn't a small cannery. It's a complex network of high-speed processing lines. The first stage inside is receiving and initial sorting. Mangoes are gently unloaded, often into water flumes or onto wide conveyors, minimizing handling damage. Workers quickly perform a visual inspection on this moving stream of fruit, manually pulling aside any mangoes that are clearly undersized, damaged, or have visible defects. Only the best-looking, apparently sound mangoes continue deeper into the automated processing heart of the factory. The main event for the vast majority of these mangoes starts on the high-speed cleaning and sorting lines. Mangoes travel along conveyors into industrial washing systems. They might pass through large water baths with controlled agitation to loosen surface dirt, followed by intense spray tunnels where high-pressure jets of water blast away any remaining soil, sap residue, and potential bacteria from the skin. These systems are built for volume, handling thousands of mangoes every hour. After washing, the fruit typically passes under powerful air blowers or over soft absorbent rollers designed to dry the surface thoroughly before the next critical step: advanced optical sorting. This is where technology takes over human vision. Mangoes roll under sophisticated optical scanners and camera arrays. These machines are incredible. They analyze the size, shape, color, and surface quality of every single mango in milliseconds, using visible light and sometimes even infrared. They can spot subtle bruises, internal defects, or ripeness levels invisible to the human eye. Based on this digital analysis, precise air jets, or small mechanical arms, automatically divert each mango onto different conveyors, sorting them by quality grade, size, and intended destination. Whether they're headed for fresh export, specific processing lines for freezing, drying, or juice, or diversion for animal feed if they don't meet any standards. These machines can sort tens of thousands of mangoes per hour with phenomenal accuracy, a true marvel of automation. Mangoes specifically selected and sorted for fresh export take a slightly different path after this. They might be individually coated with a thin layer of edible plant-based wax. This isn't for shine. It helps reduce moisture loss and extends shelf life significantly during long transport. Premium fruit can be individually wrapped in protective nets or placed in foam trays. They are then packed into sturdy cardboard boxes, often labeled with detailed traceability information, and moved into temperature-controlled cold storage rooms before being loaded into refrigerated shipping containers to travel across continents to supermarkets and retailers globally. Mangoes destined for processing, making up the largest volume on these industrial lines, hit another set of high-speed machines. First, peeling and deseeding. Automated peeling machines use rotating blades or water pressure systems to quickly strip away the outer skin while minimizing the loss of valuable flesh. Separating the fruit's cheeks from the large, awkward pit is still often a point where human skill is essential. Workers guide the peeled mangoes through specialized cutters that efficiently slice off the flesh, while machines handle the pits. It's a point where human dexterity works in conjunction with automated speed, processing mountains of mangoes at astonishing rates. From the deseeding stage, the mango flesh is directed onto various high-speed lines depending on the final product. For frozen mango, the flesh is typically cut into uniform cubes or slices using advanced high-speed blades. These pieces then enter an individually quick frozen tunnel. This is pure engineering magic. They travel on a conveyor through blasts of super cold air, flash freezing each individual piece in just minutes, often on vibrating belts designed to prevent any clumping. This rapid freezing process is crucial for preserving the fruit's texture, flavor, and nutrients, capturing the taste of summer year-round. For dried mango, uniform slices are carefully placed on trays, which are then moved into large industrial drying chambers. Here, temperature, humidity, and airflow are meticulously controlled over many hours, sometimes up to 24, depending on slice thickness and desired moisture level. This slow, controlled drying process reduces the water content significantly while concentrating the mango's natural sweetness and developing that unique chewy texture that dried mango fans love. It's a balance of time, heat, and air, managed by automated systems for consistency. For mango juice, the flesh, sometimes including parts closer to the pit for maximum yield, is sent to powerful presses and grinding machines that extract the liquid and pulp. The resulting juice mix might be filtered multiple times through fine screens or membranes to achieve the desired level of clarity, from thick nectar to clear juice. This juice often then undergoes evaporation to create concentrate, reducing its volume drastically for efficient shipping in large drums or tanks to bottling plants worldwide. At those bottling facilities, the concentrate is diluted back, then pasteurized, heated rapidly to kill bacteria and ensure safety, before hitting the final high-speed automated lines. Bottles or cartons zip along conveyors, are rapidly filled with precise volumes of pasteurized juice, and sealed tight with caps or heat seals. These lines operate at incredible speeds, processing thousands of units per hour, ensuring the juice reaches consumers safely with a long shelf life. Packaging is designed to protect the juice from light and air, preserving its color and nutrients. Throughout all these complex, interlinked processing lines, from initial sorting, cleaning, and optical inspection, to peeling, cutting, freezing, drying, juicing, and final packaging, rigorous quality control is implemented at every single stage. Samples are continuously taken and tested in on-site laboratories. Scientists and technicians check for everything: sugar content, acidity, color, texture, and, most critically, microbial safety and purity. It's a relentless process of monitoring and verification, ensuring that every mango product, whether fresh, frozen, dried, or juice, meets the stringent global standards required for millions of tons of food. So, the next time you enjoy that burst of sweet, tropical mango flavor, remember the mind-blowing industrial journey it took. From a tiny flower hand-pollinated far away, grown for months, carefully picked despite its fragility, cleaned by air and cameras, sorted by lasers, peeled by powerful machines, cut by high-speed blades, perhaps individually flash-frozen or precisely dried, or transformed into juice and sealed with precision in high-tech packaging. It's a product of global logistics, vast agricultural science, brilliant precision engineering, and skilled human touch on a scale that's truly amazing. It's a fascinating look at the hidden secrets behind an everyday pleasure. What part of this massive mango-making process surprised you the most? Let us know in the comments. Every single year, more than 20 million short tons of dairy products are produced worldwide, and Nestlé condensed milk takes a significant portion of that total. Just imagine this. Each day, over 100,000 gallons of milk arrive at the company's factories. But even the freshest milk still shows up dirty. Yes, indeed, microscopic particles of dust, feed, and even traces of blood can make their way inside. How do they turn all that into perfectly smooth, thick condensed milk that melts in your mouth? And why would it be a completely different product without those tiny lactose crystals? Watch until the very end. You will not believe what every drop goes through. Today, Nestlé is one of the leading global companies in the food industry, and its products, including condensed milk, are represented in many markets around the world. It all started in the year 1866, when the Anglo-Swiss Condensed Milk Company was founded, becoming the very first to produce condensed milk in Europe. Meanwhile, in the year 1867, the Swiss pharmacist Henri Nestl developed the first infant milk formula, which marked the beginning of the Nestlé brand. Nestlé began producing condensed milk in the 1870s, entering into direct competition with Anglo-Swiss. However, in the year 1905, the two companies united, forming one large corporation called Nestlé and Anglo-Swiss Condensed Milk Company. This move provided the impetus for rapid development of condensed milk production and export all over the world. Initially, condensed milk was positioned as a nutritious and long-lasting product that could replace fresh milk, especially in regions with limited access to high-quality dairy. Because of its prolonged shelf life and ease of transportation, it quickly gained popularity, not only among military personnel and travelers, but also in everyday family life. In the United States of America, Nestlé began its active condensed milk production at the start of the 20th century, constructing its factories and expanding its market presence. Over time, the brand came to be associated with high quality, and Nestlé condensed milk became an integral part of culinary culture, especially in desserts, baked goods, and coffee beverages. Today, Nestlé continues to produce condensed milk under different brand names, supplying markets in the United States of America and worldwide with products that combine tradition and modern standards of quality. The milk that is delivered to Nestlé factories is subject to extremely strict requirements. The company adheres to international quality and safety standards to guarantee the production of flawless products. Milk is supplied from verified dairy farms, where cows receive balanced nutrition and veterinary care. Before being sent to the factory, the milk undergoes its initial quality tests right there on the farm. The level of fat, protein, and the absence of antibiotics or other unwanted impurities are checked. Milk is transported in special refrigerated stainless steel tanks. The temperature during transportation is maintained at approximately 39 degrees Fahrenheit to preserve freshness and prevent bacterial growth. These tanks are sealed and regularly disinfected to ensure the highest standards of hygiene are upheld. Every day, around 100,000 gallons of milk arrive at Nestlé factories. Once the milk reaches the factory, it is tested again in the laboratory. Only then does it go into the main production process. The milk that makes the cut is fresh, safe, and of the finest quality. Precisely what becomes the foundation for the legendary Nestlé condensed milk. But how does it become so exceptional? An interesting fact is that no matter how perfect the process might be, the milk inevitably arrives at the factory dirty. As surprising as it may sound, the milk can contain microscopic particles that end up there during milking or transportation. These may be small leftovers of feed, dust, tiny bits of dirt from milking equipment, or other undesirable elements that are invisible to the naked eye. It is totally normal, since milk is a natural product, and these microscopic contaminants may appear during milking or storage. Cleaning and filtration are essential steps at the factory, which make the milk cleaner and safer for consumption by removing such particles. After the milk arrives, it first passes through filters that trap larger particles like hair, bits of feed, dust, or any other visible impurities. This is the primary step in getting rid of coarse debris. Next, the milk may go through a centrifuge. During this process, the milk spins at high speed, and due to centrifugal force, heavier particles like fat, impurities, or even traces of blood that might have entered the milk during milking are separated. You might wonder where blood could come from. I will explain. In a cow's body, blood is what transforms into milk in a complex biological process. Plus, an animal can have minor scrapes. Centrifugation also allows for standardizing the milk's fat content, if necessary, depending on whether high-fat or low-fat milk is being produced. The next phase is microfiltration. This is a finer filtration method that uses special membranes to remove small particles and microorganisms. It helps ensure even greater purity of the milk, which is crucial for the safety of the final product. After filtration, the milk is cooled to a low temperature, around 40 degrees Fahrenheit, to maintain freshness until further processing steps, such as pasteurization. Initially, the cleaned and cooled milk is temporarily stored in large, sterile stainless steel tanks. The pasteurization process at large factories like Nestl is fully automated. When pasteurization begins, the milk flows from the tanks to the pasteurization units through sealed pipes. These pipes are made of stainless steel, which eliminates the possibility of contaminating the milk during transfer. Before entering the pasteurization apparatus, the milk may once again pass through filters for additional removal of any small particles that might still be present. The milk is pumped through the system by pumps that regulate both pressure and flow rate, ensuring a smooth, continuous process. The milk goes directly into a plate or tubular heat exchanger, which is a specialized piece of equipment that rapidly raises the milk to the necessary pasteurization temperature. The tubes or plates are heated by hot water or steam, and as the milk passes through them, it is heated to the required temperature, for example around 167 degrees Fahrenheit. In enormous silver-colored stainless steel tanks that resemble giant gleaming columns, fresh pasteurized milk is stored. Through a network of intertwining pipes, which seem almost like steel veins, the milk travels to separators, machines that rotate at extremely high speed, creating a fascinating visual effect. Inside these machines, the milk is separated into cream and skim milk under the influence of tremendous centrifugal force, which is difficult even to imagine. The large storage tanks at factories like Nestl can hold anywhere from 5,000 to 50,000 gallons of milk, depending on the scale of production. The most common tanks have a capacity of about 30,000 gallons. On special display screens, digital readouts show the fat content, density, and temperature. Everything is under strict control. Robotic arms measure the exact amount of cream, blending it with skim milk to achieve the perfect balance. This step is reminiscent of how an artist carefully selects just the right shades of paint for a canvas. This is milk standardization. The process is automated and appears almost futuristic. Pipes carrying the milk, immaculate cleanliness, the hum of high-speed machines, and precision down to the thousandths of an ounce. The standardized milk comes out of this system, prepared for the next steps. To make sweet condensed milk, they add sugar, which can be around 40 or 45% of the mixture. Sugar here does more than just sweeten, it also acts as a preservative, helping the product last longer. The primary stage is removing excess water. The milk and sugar mixture is fed into vacuum evaporation systems, where, under reduced pressure, the blend is heated to approximately 150 degrees Fahrenheit. Thanks to the vacuum, the water evaporates quickly without scorching the milk. The outcome is a thicker mass with a significantly lower water content. about 30% instead of 87%, which is found in ordinary milk. After evaporation, this milk mass is still very hot and extremely thick. It is transferred to special cooling tanks, where cold water or a cooling fluid circulates along the walls. These are huge metal containers through which a chill seeps, almost like a gentle winter breeze. Large paddles, similar to giant mixers, slowly stir the milk, turning smoothly and steadily, so the mass does not settle or stick to the walls. The process is slightly like making ice cream. The hot mixture gradually cools down to about 90 degrees Fahrenheit. When the temperature reaches the right point, lactose crystals, milk sugar, are introduced into the mixture. These tiny, almost imperceptible particles act as seeds for the formation of thousands upon thousands of microscopic crystals in the milk mass. The milk continues to be gently stirred, and the crystals begin to grow in a very uniform way, thanks to precise temperature control and carefully managed stirring speed. If this process is disrupted, the crystals become too large, and then the condensed milk would end up grainy rather than smooth and creamy in texture. At the end of this process, the condensed milk attains the smooth, thick consistency, with a slight sheen that we all recognize. The result of perfect cooling and the meticulous handling of lactose crystals. In this way, from the chaotic ocean of hot milk emerges the sweet and tender product we know as condensed milk. Before packaging, the condensed milk is filtered one more time to remove any possible remaining unwanted particles and is tested for compliance with the standards. The finished condensed milk is packaged into cans, tubes, or pouches in aseptic conditions, sealed tightly, and then sent for cooling. Afterward, the product is ready for storage and distribution. Every year, over 150 million carats of diamonds are mined worldwide. But did you know that some mines are so deep that the temperature inside exceeds 110 degrees Fahrenheit, and powerful explosions can cause seismic tremors felt up to 50 miles away? Diamond mining isn't just digging. It's a full-scale scientific operation that starts with satellite analysis and can last for decades. How are these precious stones found? How do drilling rigs reach depths of 10,000 feet? And what happens to diamonds after they're mined? Let's break it down together. Diamonds form deep beneath the Earth's surface and are brought up through volcanic processes that create Kimberlite pipes. These pipes, made of ancient igneous rock, are the primary sources of diamonds and can reach depths of over 10,000 feet, with temperatures inside the mines exceeding 110 degrees Fahrenheit. To cool these environments, powerful ventilation systems compress air. In some mines, the air is so pressurized that if a door between compartments is suddenly opened, the wind force can knock a person off their feet. Sounds dangerous, right? Before mining begins, geologists conduct extensive exploration that can last for decades. The process starts with analyzing satellite images and aerial photography. This is followed by field studies, where geologists collect rock samples for chemical analysis. Special attention is given to the presence of indicator minerals like garnets, ilmenite, and pyrope, which suggest the potential presence of diamonds. If the exploration yields positive results, detailed surveying begins. Drilling rigs create boreholes up to 10,000 feet deep, extracting core samples, cylindrical sections of rock. These samples undergo thorough laboratory analysis to assess the diamond content in the rock. Geophysical methods like magnetic surveys, electromagnetic scanning, and gravimetry are used. Open pit mining is employed when the deposit is relatively close to the surface. Underground mining is used if diamond-bearing rocks are located at significant depths. Mine shafts are constructed, allowing workers and equipment to descend. Mining begins with drilling boreholes into the Kimberlite rock. For this, massive drilling rigs over 50 feet tall are used. Each borehole can reach lengths of 2,000 feet, and a single mine may have tens of thousands of such holes. After drilling, explosives are placed in the boreholes, and the detonation occurs under strictly controlled conditions. Some diamond mines use such powerful explosives that underground blasts can trigger minor seismic tremors detectable over 50 miles away. First, vertical shafts are dug, reaching depths of over 10,000 feet. The diameter of the main mine shafts often exceeds 20 feet. Additionally, horizontal tunnels are constructed, stretching for several miles. After the explosion, the rock in the mine breaks into pieces of various sizes, from large boulders to fine gravel. Powerful loaders with buckets lift the debris and transport it to central transfer points. Here, massive dump trucks, each capable of carrying over 250 tons of rock, load the extracted material and deliver it to the main tunnels. In some mines, instead of trucks, specialized electric trains running on tracks tens of miles long are used, capable of transporting over 500 tons of kimberlite rock per trip. The main tunnels are equipped with conveyor systems that start at depths of several thousand feet and extend to the surface. The length of these belt conveyors can exceed 15 miles, with belt widths over 6 feet. Some systems have multi-level structures, allowing simultaneous material transport from different parts of the mine. Before being placed on the conveyor, large rock fragments pass through crushing stations, where massive steel rollers over 20 feet long break the debris into fragments no larger than 3 feet in diameter. The crushers operate with compressive forces of tens of thousands of pounds per square inch and can process over 10,000 tons per hour. After initial crushing, the material is loaded onto the main conveyor belts, which transport it to the washing system. In some sections, the conveyors pass through special grottos equipped with giant sieves with holes of various sizes. During transport, smaller rock particles are sifted and directed to separate processing lines, while larger pieces move to the next stage of crushing. The newest mines are equipped with automated control systems that analyze the rock composition in real time and adjust conveyor speed and crushing intensity. As the future diamonds approach the surface, they are fed into special bunkers where the rock accumulates, ready for further processing. The capacity of these bunkers can exceed 100,000 tons, and their structure allows for even material distribution to washing and sorting facilities. In mines located in deep regions, transporting the rock can take several hours, with annual extraction volumes reaching millions of tons. When I was a kid, my family loved going to the beach. It didn't happen often. My dad rarely had time off. But when it did, everyone was thrilled and happy. Diving underwater to find seashells, crabs, or even clams, I never imagined that diamonds could be mined from the sea. Deep sea diamond mining is one of the most complex and technologically advanced methods in the mining industry. Mines are located where kimberlite pipes or alluvial deposits lie beneath the ocean floor at depths exceeding 500 feet. Geologists begin by conducting surveys using underwater drilling rigs. These rigs are stationed on specialized offshore platforms or vessels equipped with computerized navigation systems for precise positioning over potential deposits. Once diamond-bearing deposits are confirmed, the construction of an underwater mine begins. This is a complex process involving the creation of sealed tunnels or the use of massive drilling capsules operating under high pressure. One method involves using giant seabed drilling complexes, which can exceed 200 feet in length and weigh over 5,000 tons. These complexes are equipped with diamond-tipped drills capable of cutting through even the hardest rock. During drilling, a specialized hydraulic system creates a water flow under pressures exceeding 3,000 pounds per square inch, washing out small rock particles and diamonds into special reservoirs. Another method uses giant underwater vacuum systems that can descend to depths of up to 1,000 feet and suck up hundreds of thousands of cubic feet of rock per hour. The material is then brought aboard a vessel or platform for initial processing. Special underwater crushers can process up to 50 tons of kimberlite rock per hour. Powerful pumping systems are used to transport the rock to the surface, capable of moving up to 1 million gallons of water per day. Streams of enriched rock are directed through pipelines that can stretch for several miles. The material then enters large sorting tanks, where it passes through gravity separators. Heavier diamonds settle at the bottom, while lighter particles are washed away and returned to the sea. Remotely operated underwater vehicles play a crucial role in deep-sea mining, operating at depths of up to 10,000 feet. They are equipped with manipulators that can precisely collect large diamonds directly from the seabed. Their high-resolution cameras allow operators, located hundreds of miles away, to control the process in real time. Deep-sea mining is so complex and costly that only a few countries in the world have the necessary technology. It can cost hundreds of millions of dollars, and the full mining cycle can take over 10 years. Despite the challenges, this method yields millions of carats of diamonds annually, supplying the global market with precious stones hidden in the ocean's depths for billions of years. On the surface, the extracted rock is crushed in processing plants, where massive steel jaws over 20 feet long break the stones into fragments smaller than 2 inches. Each plant can process over 10,000 tons of material per day. After crushing, the rock passes through a series of washing tanks filled with water and chemical reagents. Diamonds, which have high density, settle at the bottom, while lighter minerals are washed away. Once the material is on the surface, specialized X-ray separators are used to identify diamonds based on their ability to fluoresce under ultraviolet light. Magnetic separators work by exploiting differences in the magnetic properties of materials. Diamonds are non-magnetic, while most minerals in Kimberlite rock have weak magnetic properties. In these systems, the rock is fed onto rotating drums over 20 feet long, which generate strong magnetic fields exceeding 10,000 Gauss. Magnetic mineral particles stick to the drum's surface and are removed into a separate container, while diamonds and non-magnetic rock residues move forward. X-ray systems are used in the next stage, when the rock is already significantly purified. These systems rely on diamonds' unique ability to fluoresce under X-ray radiation. The stones enter a special tunnel where they are exposed to X-rays with energies of up to 200 kiloelectronvolts. The diamonds begin to glow, and highly sensitive optical sensors instantly detect their location. The system then activates a high-speed air jet operating at pressures exceeding 100 pounds per square inch, which literally blows the diamonds out and directs them into a collection container. The cleaned diamonds are sorted by size, quality, and color. The sorting process is fully automated and managed by operators in specialized control centers. Each operator monitors dozens of X-ray systems using high-resolution computer panels. Modern systems use machine learning algorithms that can adjust equipment parameters in real time for maximum efficiency. If malfunctions or deviations occur, operators can manually change settings or redirect material flows for reprocessing. A single system can process up to 20 tons of material per hour, with precision that detects even the tiniest diamonds smaller than 1/10 of an inch. At large diamond mines, dozens of such systems operate simultaneously, extracting hundreds of millions of carats annually. After sorting, the diamonds are sent for cutting, where artisans use lasers and mechanical tools to transform them into precious gemstones. Once cut, they enter the market, sold as part of jewelry or used for industrial purposes. This was the most unusual tour in the history of this channel. When I first heard about the Envylight farm, a place where they grow black soldier fly larvae for animal feed, I imagined something straight out of science fiction or a horror movie. But what I saw wasn't just fascinating, it was revolutionary for the future of feed. I never thought raising flies could be this exciting. Yes, you heard that right. Flies. Got questions? Of course you do. Stick around to get all the answers. Let's start with the basics. What exactly are black soldier fly larvae, and why are they so special? So, the black soldier fly? Not some action hero from a movie, but a small insect called Hermetia illucens, addresses two major challenges of our time: the feed shortage and the environmental crisis. Its larvae are tiny protein bombs. These creatures consume organic waste and turn it into high-quality feed for fish, poultry, and even pets. Larvae can process up to 110 tons of organic waste on just 2.5 acres of production space in a single month. What's more, they use 47% less water and produce 200 times less carbon dioxide than traditional livestock. Envylight is one of the first companies to scale up this process. I visited their farm and saw firsthand how this ecosystem works. Imagine massive rooms filled with trays of larvae. Smelly? Sure, a bit, but it's more the smell of change, and I'm not exaggerating. The idea of using insects as a protein source didn't just come out of nowhere. It stemmed from global problems that have been brewing for decades: population growth, resource shortages, and the massive environmental toll of traditional livestock farming. But how did humanity come up with the idea of farming flies? People have been eating insects for thousands of years. In many parts of Africa, Asia, and Latin America, it's a normal thing. But until the 20th century, The concept of using insects as feed, instead of food for humans, was almost unheard of. Let's be honest, who would have thought, hey, let's raise flies to feed chickens? The first wave of interest in insects came in the 1960s. Scientists started noticing that insects could be a protein source requiring minimal resources. But the idea didn't take off back then. People still relied on traditional methods: corn, soy, and fish meal. Then the modern environmental crisis emerged, forcing researchers to look for alternatives. The Hermetia illucens larvae became the star for a reason. Imagine this: the fly doesn't spread diseases, doesn't buzz around your house like a common housefly, and most importantly, its larvae can digest nearly any organic waste. It's the perfect little recycler. Interestingly, serious research into larvae started in the 1990s, and guess who funded it? Waste management companies. They were looking for ways to reduce the volume of organic waste ending up in landfills. It turned out that black soldier fly larvae could destroy up to 60% of organic material, converting it into protein and fats. That's when scientists thought, what if we used this for animal feed? Around the mid-2000s, the idea of insects as feed began gaining momentum. Picture startup founders in labs figuring out how to grow larvae on an industrial scale. They saw the growing demand for farmed fish and understood, if we don't find an alternative to fish meal, ocean ecosystems are doomed. The first successful projects appeared in Europe and the United States. One of the pioneers was Envylight, which launched the concept of growing black soldier flies on organic waste. Their approach was simple yet brilliant. They created a closed-loop ecosystem where organic waste was transformed into feed, and leftover larvae were used as fertilizer. Let's talk about fish feed because this part really blew my mind. Did you know most fish feed is made from fish meal? Every year, over 15 million tons of wild fish are caught to produce feed for aquaculture. That's an enormous blow to marine ecosystems. Black soldier fly larvae provide an alternative that not only reduces dependence on fish meal, but also helps preserve oceanic fauna. For instance, 1 ton of larvae can replace over 2 tons of fish meal. That's equivalent to saving nearly 5 tons of wild fish. Envylight raises larvae in controlled conditions where they feed on organic waste, leftovers from fruits, vegetables, or even coffee grounds. It's essentially a farm where the animals are tiny but incredibly productive larvae. They're fed, cared for, and when they reach a certain age, harvested, dried, and turned into feed. By the way, the entire process is designed to minimize environmental harm. From every 2 pounds of larvae, you can get over 10 ounces of high-protein feed. For comparison, raising pork requires about 13 pounds of feed to produce just 2 pounds of meat. Here, we've got a product that's several times more efficient than livestock farming. A lot of people are skeptical about the idea of feeding cats or dogs insects. But here's an interesting fact. According to a 2022 study, over 60% of pet owners in the United States are willing to buy pet food made from eco-friendly protein sources, including insects. Black soldier fly larvae have already been included in many premium pet foods. Their protein is not only nutritious, but also hypoallergenic. This is crucial for pets with sensitive stomachs or allergies to standard feeds. When I first heard the buzzing of these flies on the farm, I felt something strange. A bit unusual, a bit eerie, but mostly awe. This is the future we're building right now. I still think this process looks a bit futuristic, but if it's what will save our oceans, feed millions of pets, and make our planet better, I'm all in. How about you? Ready to support the idea of larvae in feed? It's good that humanity finally realizes how much traditional livestock farming drains the planet. For example, raising 1 cow costs the world more water and resources than an entire facility of larvae. People increasingly want to make eco-friendly choices, even in pet food. It's predicted that by the year 2050, Earth's population will grow to 10 billion. Finding new food sources isn't a luxury, it's a necessity. Does this kind of farming have a future? Let me answer that with another question. Does our planet have a future? Because if we don't switch to more sustainable food sources, we're in serious trouble. Right now, farms like Envylight operate in over 30 countries, including the United States, the Netherlands, China, and South Africa. It's estimated that by the year 2030, the insect feed market will grow to $8 billion. Honestly, there's a certain irony to this. We spent hundreds of years trying to get rid of flies as pests, and now it turns out they might save our planet. Life loves surprises, doesn't it? From the outside, a farm like this looks like a cross between a factory and a greenhouse. The main building is modern, clean, and sterile. It's not a chaotic mess, but a high-tech space. The trays of larvae resemble multi-tiered shelves in a library, but instead of books, there are containers filled with wriggling larvae. Automation systems, robots and sensors, control everything from climate to the amount of food for the larvae. This farm isn't a chaotic swarm of flies and larvae. It's a structured system designed for maximum efficiency in farming and processing. It all starts in the fly room. This is a large space with special lighting and temperature control. Soldier flies buzz around in mesh containers or specially designed enclosures. They look pretty unremarkable. Black, medium-sized, with long wings. The room maintains a warm, humid climate, perfect for breeding. The main goal here is to give the flies a place to lay eggs. Female flies deposit thousands of tiny eggs into special containers. These containers are wooden or plastic panels with small holes. The eggs are then moved to incubators, basically warm shelves, where temperature and humidity are kept optimal. Within a few days, tiny larvae hatch from the eggs. Next, we move to the larva rearing sector. Rows of trays or containers are filled with organic waste, leftover food, vegetable scraps, grain byproducts, and more. In these trays, larvae crawl around, growing at an incredible rate. They look like tiny, creamy worms that literally turn waste into protein mass. Automated systems for feeding and monitoring are often used here, with special sensors tracking temperature, humidity, and even the larvae's appetite. When the larvae reach the right size, they are harvested using specialized sieves or automated conveyors. Then they undergo processing. The larvae are dried at high temperatures or frozen to preserve nutrients. The dried larvae are ground into powder or pellets, which become the basis for feed. Besides protein, larvae are rich in healthy fats. These fats are extracted using presses and used in feed or for industrial purposes. In the finished goods warehouse, protein powder, fats, and other products derived from larvae are stored before being shipped to buyers. Did you know that over 3 billion cans of preserved peaches are produced globally every year? But how do peaches go from orchard trees to perfect slices in syrup that we all love? From harvest to sealing freshness in cans, this is a high-tech process where every second counts. Imagine a factory filling up to 30,000 cans per hour. Ready to peek behind the scenes of this amazing production? The journey of canned peaches begins in meticulously cared-for orchards. And here is something important. Specific varieties of peaches are chosen for canning. Picture a tree bred to prepare its fruit for a long life in a can. These peaches are cultivated with taste, firmness, and shelf life in mind. They are not just pretty, they are strategically important. These orchards are typically located in regions with warm climates and plenty of sunshine. Peaches love the sun. It is like their secret ingredient. The main peach-growing regions are found in areas with mild and warm climates. California, Georgia, and South Carolina lead the United States in peach production. Among other countries, Italy stands out, especially northern Italy, where a combination of mountains and valleys creates the perfect climate. China is another major global producer. Peaches are grown in nearly all its provinces. Depending on the country, peach orchards can range from a few acres on small family farms to hundreds of acres for industrial producers. In California alone, orchards designated for canning peaches span over 25,000 acres. In Italy, the total area for peach cultivation is approximately 170,000 acres, though not all are used for processing. Growing peaches is a true art. Here are a few key challenges. While peaches thrive in warmth, Severe frost can destroy buds or even entire trees. Therefore, cultivating peaches requires careful selection of varieties suited to the local climate. These trees need regular irrigation, but too much water can cause root rot. Fungal diseases like leaf curl and pests such as aphids require constant monitoring and treatment. Peach trees also need annual pruning to ensure optimal fruit growth. This is a complex but essential process. Additionally, peaches must ripen on the tree to be sweet and juicy, but they cannot overripe, as they become too soft for transportation. This means harvesting occurs on a very tight schedule. Most orchards for canning work with peach varieties that have slightly thicker skins and firmer flesh. This allows them to better withstand processing and transportation. Some farmers grow organic peaches, free from pesticides and chemicals. This is more challenging, but results in a premium product that is increasingly popular. Caring for peach orchards is not just work, it is a science. And though it is not easy, the result is fragrant, juicy peaches that we can enjoy even on cold winter days. Harvesting peaches can be mechanized. Tractors with special shakers gently shake the trees, and the fruits fall onto special mats. However, the most delicate varieties are harvested by hand to avoid damage. Did you know that every picked fruit reaches the factory within 24 hours? Here, every minute is worth its weight in gold. Once the peaches are harvested, their journey has just begun. Transporting them to the factory is a crucial stage because these fruits are incredibly delicate. To preserve their appearance and quality, strict rules must be followed. Right in the orchard, the harvested peaches are usually sorted. Damaged or overripe fruits are discarded as they can spoil during transportation. Peaches are packed into small boxes or plastic containers designed to minimize pressure. Often, they are lined with soft materials to avoid damage during transit. Since peaches spoil quickly, they are delivered to the factory as soon as possible, usually within a few hours of harvest. Factories are often located near the orchards to reduce travel time. Refrigerated trucks maintain temperatures at a maximum of 40 degrees Fahrenheit to slow the ripening process and reduce the risk of spoilage. In large operations, specialized systems gently move the fruits into containers. This reduces the risk of mechanical damage and minimizes manual labor. Every minute counts. If the peaches are delayed, they can begin to spoil or lose their appearance. Excess moisture can lead to rot, while insufficient moisture can cause the fruits to dry out. Therefore, containers and vehicles are equipped with systems to regulate these parameters. Each peach is, essentially, a delicate fruit that is easily damaged. Thus, they are packed carefully, with no unnecessary pressure. In some countries, like Italy or the United States, orchard owners use electric mini-tractors to transport fruits from the orchard to intermediate storage. This is more eco-friendly and convenient. Farmers sometimes organize delivery at night or early in the morning when it is cooler. This helps keep the fruits fresh until they reach the factory. In large operations, transportation containers are labeled, so the factory knows exactly which orchard each batch came from. This helps track the quality of every harvest. As soon as the truck with peaches arrives at the factory, the fruits are immediately inspected for freshness and integrity. Those that pass inspection are sent to the first processing stage, washing and cleaning. And yes, this process happens as quickly as possible because freshness is the key to perfect canned peaches. Workers or automated systems quickly inspect the fruits to remove damaged, rotten, or overly ripe ones. Large operations use optical scanners to analyze the external appearance based on color, shape, and defects. Honestly, I would already be exhausted by the endless inspection, and this is just halfway through the peach's journey to store shelves. Even with modern technology, the human factor remains critical. Operators stand by the conveyor belt and pick out fruits that fail the automatic check. Sometimes, only a human eye can catch subtle defects. The fruits are weighed since overly small or underdeveloped ones may not meet canning standards. Washing is not just rinsing with water, but a full-fledged technological process. Peaches are harvested in orchards, where they can pick up dust, soil residues, or even chemical plant care products. After inspection, the fruits enter special rotating drums, where they are gently rinsed with water. Warm water with mild cleaning agents is used to remove even the smallest particles of dirt. Before peeling, peaches are rinsed again, this time with clean water without any additives. By the way, this entire process takes just a few minutes. Next, peaches are immersed in hot water or exposed to steam for a few seconds. This softens the skin, making it easy to remove. This method also helps preserve the texture of the flesh. Then, the peaches go to special machines equipped with rotating brushes or knives that carefully peel them. The goal is to avoid damaging the fruit and preserve as much flesh as possible. The next step involves removing the pits. Special devices carefully cut the peach in half and extract the core. But even here, there are nuances. Some peaches, known as clingstone, have pits that cling tightly to the flesh. These require more precise equipment. Peeled peaches undergo a final check to ensure the skin is completely removed and the fruit's shape is intact. This is especially important for canned peaches made from halves or quarters. After peeling, peaches are cut into halves, slices, or even cubes, depending on their intended use. Here, specialized machines with incredible precision come into play. Did you know some factories have blades that can slice peaches faster than you can blink? Even so, each slice is manually inspected to ensure no defects are missed. Next, the peaches are placed in cans and syrup is added. Depending on the recipe, the syrup can be light, medium, or thick. The most interesting part is that some recipes use special flavorings to enhance the taste of the peaches, and this is the detail you definitely notice when you open a can. The cans are sealed and immediately pasteurized. This means they are heated to high temperatures, which lock in freshness. During pasteurization, canned peaches are heated to approximately 200 degrees Fahrenheit. This temperature range is high enough to destroy harmful microorganisms, preserve the product's freshness, and extend its shelf life, but it does not affect the taste or texture of the peaches. By the way, the entire process takes just a few minutes, leaving no chance for bacteria. The speed of filling cans can reach from 3,000 to 30,000 cans per hour. This demonstrates the high level of automation and efficiency in such productions. After cooling, the cans are sorted, labeled, and sent to warehouses. Sometimes, they even undergo additional inspections, to make sure everything is perfect. Then these cans are shipped to stores worldwide. Did you know the United States, China, and Greece are the 3 largest producers of canned peaches? Additionally, global tasting competitions are held to select the best syrup. Yes, this industry has its own Oscar. So next time you open a can of peaches, remember how many people and machines worked to bring this dessert to your table. You know what? They really nailed it. Imagine this. Every single year, all around the world, over 70 million automobiles are manufactured, and each one of them demands high-technology glass. From the broken flask with nitrocellulose that accidentally revealed laminated glass, to the powerful hydrophobic coatings, the history of this material is truly astonishing. Today, we are going to learn how glass becomes ultra-strong, safe, and prepared to protect us from wind, rain, and the dangers of the road. Please get ready for a journey into the realm of advanced modern technology. Thousands of short tons of glass scrap are recycled in order to create crystal clear windows for automobiles. It is not only about safety, but also about saving precious resources. And that is just the beginning. The history of automobile glass production is closely linked to the development of the automobile industry, which emerged in the late 19th century. The glass used in today's automobiles has undergone a long path of improvements that have made it safer, stronger, and more functional. When the very first automobiles began to appear, they were initially not equipped with any glass at all. The open body design offered only partial protection to passengers, while dust, wind, insects, and other hazards made traveling extremely uncomfortable. Later on, when automobiles became faster, the need for driver and passenger protection emerged. Windshields were first made from ordinary window glass, which, although it provided some degree of protection, had a serious drawback. In accidents, it would shatter into large, sharp fragments that resulted in numerous injuries. The first groundbreaking discovery in the field of automobile glass was the creation of laminated glass. This happened by chance. In 1903, a French chemist named Edouard Benedictus accidentally dropped a flask coated with nitrocellulose. The glass cracked but stayed in one piece, thanks to the thin layer of plastic. This accident inspired the scientist to develop a multi-layered glass, which later became the basis for triplex. By the 1910s, laminated glass was already being used in premium class automobiles. Its construction consisted of 2 layers of glass with a thin, transparent film in between them. In the event of impact, the glass did not scatter, and cracks remained on the film. In the 1920s, laminated glass began to be widely used in the production of windshields. Its main advantage was increased safety. Even in serious accidents, the fragments did not fly apart, but remained embedded in the polymer layer. The next stage in the evolution of automobile glass arrived in the 1930s, when the technology for making tempered glass was patented. This material was produced by heating the glass to high temperatures followed by a rapid cooling. As a result of such a process, the glass became stronger, and upon breaking, it would fracture into small pieces with dull edges, minimizing injuries. By the middle of the 20th century, tempered glass was being used for the side and rear windows of automobiles. It was less expensive to manufacture compared to triplex and provided a sufficient level of safety for those parts of the vehicle. In the 1950s and 1960s, automobile glass became even more advanced thanks to ongoing technological progress. During this time, several important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and more durable. Mass production. The automation of manufacturing processes drove down the cost of automobile glass, making it more affordable for a wide range of consumers. Coatings for sun protection. Special coatings that blocked ultraviolet rays and reduced the heating of the automobile cabin were used for the first time. One of the most significant technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, enabled the manufacturing of perfectly smooth glass by allowing molten glass to spread across the surface of molten tin. Through this method, the glass became more uniform, stronger, and better suited to mass production. Even today, the float method remains the foundation of automobile glass manufacturing, ensuring precise dimensions, a smooth surface, and high quality. In the second half of the 20th century, automobile glass underwent even more changes aimed at improving both safety and comfort. In the 1960s, heating filaments began to be installed in the rear window of automobiles, preventing condensation and freezing. In the 1980s, glass was introduced with special metallic coatings that reflected sunlight and reduced heat buildup inside the vehicle. Glass with ultraviolet protection. With the introduction of new technologies, automobile glass began providing virtually complete protection from harmful ultraviolet radiation. And now, we enter the modern period of automobile glass production, which we will discuss at this very moment. We shall start with the glass used in automobiles. Automobile glass is divided into several types, depending on its purpose and manufacturing technology. Windshield. This is usually multi-layered glass composed of 2 sheets of glass with a polymer film between them. This design ensures that, if damaged, the glass does not break into sharp fragments. Side and rear glass. Most often, this is tempered glass, which, upon impact, fractures into small, blunt-edged pieces that reduce the risk of injury. Panoramic roofs, or other special types of glass, often use laminated or tempered glass with specialized coatings for protection against ultraviolet radiation. The main components of glass are natural materials, which are mixed in certain proportions to achieve the desired properties. Quartz sand is the principal element in glass, giving it transparency. It must be extremely pure and contain minimal impurities. Soda is added to lower the melting temperature of glass. Lime improves the mechanical durability and chemical characteristics of glass. Additional additives. These are used to adjust color, transparency, resistance to ultraviolet light, and other properties. The raw materials are cleaned, dried, and ground to a uniform state. It is crucial to eliminate as many impurities as possible, as they can affect the quality of the glass. After preparation, the raw mixture is poured into special furnaces for melting. This stage includes a few important steps, so let us review them together. Melting temperature. To create molten glass, a temperature of about 2,732 degrees Fahrenheit is used. Throughout the melting process, the raw materials transform into a uniform, viscous liquid. Homogenization. The molten glass is stirred to distribute components evenly. This is important for preventing air bubbles or other irregularities in the finished product. The furnaces for melting glass are equipped with modern systems for temperature control and process automation, which guarantee the high quality of the final product. After melting, the molten glass proceeds to the forming stage, most commonly performed using the float method in modern manufacturing. Feeding the molten glass. The liquid glass flows from the furnace onto a bath of molten tin. Due to the high density of tin, the molten glass spreads out uniformly across its surface. Under its own weight, the glass forms a perfectly even and smooth surface. Gradually lowering the temperature makes the glass grow solid. By the time it leaves the tin bath, it is ready for further processing. The float method allows the production of glass sheets with precise geometric parameters and a very high quality finish. Once it is cooled, the sheets of glass are cut to the sizes required for automobile manufacturing. Automated cutting machines ensure accuracy, and to prevent chips or cracks, the edges of the glass are polished. Every sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automobile glass, it undergoes the process of tempering. The glass is heated to a temperature of around 1,112 degrees Fahrenheit. Then the surface is quickly cooled by air jets, while the inner layers cool more slowly. As a result, stress is created, which greatly increases impact resistance. Tempered glass, when broken, shatters into small, safer fragments, minimizing the risk of injuries. After that, for the windshield, a triplex construction is used, which is a combination of glass and polymer film. Its fabrication involves several steps. Layer bonding. A polymer film is placed between two sheets of glass. The construction is placed into a vacuum press to remove air bubbles. Then the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure, ensuring a strong bond between the layers. Triplex has high impact resistance, and if damaged, the fragments stay attached to the polymer film, thus providing safety for the driver and passengers. Afterward, to enhance the properties of automobile glass, various coatings are applied. Anti-glare coatings reduce glare from the sun or from other vehicles' headlights. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings allow water to bead and roll off the glass surface. Heating elements. Thin heating filaments can be embedded in the windshield, making it easier to remove ice or condensation. To achieve the required shape, special thermoforming equipment is employed. The glass is heated to a temperature at which it becomes pliable, and it is then molded according to specified parameters. And here we arrive at the final stage. During this stage, each piece undergoes a thorough inspection. The transparency is tested, and any defects are identified. Next, the glass is tested for impact resistance and durability under load, compliance with standards, the accuracy of dimensions, the shape, and other parameters are verified. Then the finished automobile glass is packaged in a manner that prevents damage during transportation. It is delivered to automobile factories or service centers, where it is installed in vehicles. The production of automobile glass is a high-technology process that brings together physics, chemistry, and engineering. Thanks to advanced technologies and strict quality control standards, automobile glass ensures safety, comfort, and longevity. And just imagine how many stages automobile glass must go through so that we can watch over road safety and admire wonderful vistas along the way. I find it remarkable. Do you also think so? You?